Hello students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss about the frequency hopping spread spectrum. Earlier we discussed about the direct sequence spread spectrum. So before that, what is the spread spectrum? How this spread spectrum is useful in our daily life? It is all discussed in the last topic. Today we are going to discuss about frequency hopping spread spectrum and what is the PN sequence and how to generate, and what are the characteristics of this PN sequence that we are going to discuss in this topic. Okay, so coming to the course outcome, so this topic coming to the module 5 and which covers this CO5. So the course outcome 5 is identify the importance of spread spectrum techniques for secure digital communication systems. So here we given the spread spectrum techniques are used for the secure digital communication system. Okay, so our aim is here providing the secure communication. Why? Earlier the digital communication is used for the bandwidth, data rate. So that's what we're going to discuss, how the spectrum is utilized. So what are the techniques to utilize the spectrum? That's what we discuss. But here we are going to provide a secure communication. Okay. So coming to the topic. So spread spectrum. So already we discussed in the last video. But once again, what is spread spectrum? We are going to see. So spread spectrum refers to a system originally developed for the military applications to provide secure communications by spreading the signal over a large frequency band. So that means here the signal is a narrow band signal. So just like it is a narrow band. So here we are going to spreading this like a large frequency band. Okay. So the spread spectrum is a technique whereby an already modulated signal is modulated a second time in such a way as to produce a waveform which interferes in barely noticeable way with any other signal operating in the same frequency band. So here the spread spectrum is nothing but double modulation. Already it's modulated, again we are going to modulate the second time. Why? In the first slide we discussed, we are going to broaden the spectrum. That is, I am going to widen the spectrum. So that is, we are going to increase the frequency range by double modulation. Okay. So here this is a frequency hopping spread spectrum. So frequency hopping spread spectrum is a transmission technique where the carrier hops from frequency to frequency. So what is our aim? To provide a secure communication by using the spread spectrum. So if any intruder or interferer which is going to hack our signal, which is try to hack our signal, then the carrier is going to hop. That is, it jumps from one frequency to another frequency. We are in the same frequency, then it is easy to catch, or just it may be called technically hack. But when the carrier hops from one frequency to another frequency, so it is difficult to the hacker to hack your signal. So that is the frequency hopping spread spectrum. Is a transmission technique where the carrier hops from one frequency to another frequency. That is, it jumps. The carrier jumps from one frequency to another frequency. So a common modulation format for frequency hopping systems is that M-array frequency shift key, M-array frequency. So you know that the difference between M-array and binary. So what is binary? We can send either one bit, either 1 or 0. That is binary. and you can send more than one bit. That is go for the IARE technique. So earlier we discussed the binary types are ASK, FSK, PSK. Whereas in IARE, according to the syllabus, that is QPSK, quadrature phase shifting keying. So in quadrature phase shift keying, we can send 2 bits at a time, that you can call as D bit. So here you can sending more than 1 bit. So that is it is going to utilize the spectrum also. So in the place of 1 bit, I am sending 2 bits at a time. So that is IARE. So for a frequency hopping system, we are using this IARE frequency shift keying. So the combination of these techniques is referred to as FH or MFSK, frequency hopping, IARE frequency shift keying. So this is a combination. Okay. Now the frequency hopping categorized into slow hopping and fast hopping, which by slow hopping, more than one data symbol is transmitted in same channel, and fast hopping frequency changes several times during one symbol. So hopping is nothing but jumping. So the carrier jumps from one frequency to another frequency. So that is our FH. Again FH, we are having slow hopping and fast hopping. So fast hopping means the frequency changes is several times, whereas in slow hopping it is just only one. So that is slow hopping and frequency fast hopping. So now slow frequency hopping. The slow frequency hopping is a process of changing the radio frequencies of a communications on a regular basis. So slow frequency hopping is used to reduce the effects of signal fading and to minimize the effects of interference from radio channels that are operating on the same frequency. So here we're going to see how this slow frequency hopping is going to done, and what is the symbol rate. So in this slide, in slow frequency hopping, the symbol rate RS of the MFSK signal is an integer multiple of the hop rate, that is RH. So the RS is greater than equal to RH. That is symbol rate must be greater than or equal to the hop rate. So that is several symbols are transmitted on each frequency hop. So this is the slow frequency hopping. And coming to the block diagram of the transmitter. So this is the transmitter of this slow hopping. So here you can see in this picture we're having a FSK modulator. Why? Already we said that is FH MFSK signal. So the combination of frequency hopping and MFSK, the combination of FH MFSK. So the general idea or general motto of this spread spectrum is double modulating. So that means already modulating signal is going to modulating again. So simply we can call it as a double modulation. So for the first, the binary data is taken from the left hand side. So the binary data is maybe 1, 0 like this, and the modulator is here FSK is nothing but IARE FSK. Already you know that the frequency shift key, how the frequency is changing, already you know. So here I'm using a carrier. So this is the first modulation. So after the IARE FSK modulation, the signal enters into the mixer. So the mixer having the combination of product modulator and band pass filter. So the combination here you can shown as the mixer, and one input to this mixer is the frequency synthesizer, and the frequency synthesizer is taking the signal from the PN code generator, is nothing but a pseudo noise code generator. So this is a pseudo noise code. By using the pseudo code, the frequency synthesizer is going to produce the signals. So first we know the principle of frequency synthesizer. The frequency synthesizer is a circuit which is going to produce a range of frequencies by using a reference frequency signal. By using one frequency reference signal, it is going to generate a range of frequencies. Okay, so this signal, the output of the frequency synthesizer, is applied to the mixer. So here you can see in this transmitter, the up conversion is going to done. That means the frequency range is going to increase. Why? The first modulation, the frequency is going to increase. Again, here we are increasing the frequency. So this, the mixer here duty is going to up conversion of the frequency. And the final output signal is the FH MFSK. It is a frequency hopping IARE FSK signal is produced. So this is transmitted to the channel. Okay. And how this successful k-bit segments of PN sequence drive the frequency synthesizer, which enables the carrier frequency to hop to the power of k distinct values. To the power of k distinct values. There is 2 power k. So on a single hop, the bandwidth of the transmission signal is same as that of resulting from the use of a conventional MFSK with an alphabet of m equal to 2 power k orthogonal signals. Why? So this is M array. Already know m is 2 power k. So k is a number of bits we are going to transmit at a time. Okay. However, a complete range of 2 power k frequency hops the transmitted FH by MFSK signal occupies much larger bandwidth. So that is our aim. Our aim is fulfilled. Why? My aim is to broaden the signal. So that is the spread spectrum. The narrowband signal is going to widen. So why I am going to widen? By up conversion of the frequency by using a mixer, or you can say the double modulation. So already modulated signal, I am going to modulating again. Then the frequency range is going to increase. So that is a larger bandwidth. So whenever the larger bandwidth is available, so the person who are going to catch or try to catch the signal is going to more difficult. So that is why. Okay. Now this is the receiver. So this is my receiver. So here I am received. What I received? I received this frequency hop MFSK signal. So frequency hop MFSK. So now in the first block is nothing but the mixer. So again here we are using the same whatever used at the transmitter, the frequency synthesizer and local PN code generator. Why? So this we can use the same pseudo noise sequence. What we use at the transmitter, the same as used at the receiver also. So as the transmitter, the up conversion frequency is done. Now here I am going to down conversion. That means I am going to reduce this frequency range and apply to the non-coherent IARE FSK detector, and finally it is going to estimate our binary data. So the binary data is maybe 1 0 like this. Why? At the transmitter I am using the same binary data. At receiver also I recover the same binary data by using this non-coherent IARE FSK detector. Okay. So here to going to implement this non-coherent IARE detector, we use a bank of M non-coherent matched filters, each of which is matched to one of the MFSK tones. So tones means here the frequencies. Why is the frequency shift keying? So 1 and 0 have different frequencies. Okay, an estimate of the original symbol transmitted is obtained by selecting the largest filter output. So just like an in getting the optimum signal. So the match when the filter is going to match it getting the maximum signal. So it's selecting the largest filter output. Okay. So the fast frequency hopping. So earlier we discussed the slow frequency hopping. Now fast. So in slow FHMF system, the bitrate RB of the incoming bitrate or incoming binary data, the symbol rate to RS of the MFSK signal, and you can say the chip rate RC and the hop rate to RH. So there is a relation how these four is going to relate it. There is RC, that is RC is nothing but chip rate, which is equal to RS. RS is the symbol rate, that is equal to the bitrate by K. So what is K? K is nothing but log to M, and that is greater than equal to RH. RH is the hop rate. So the bit rate or the symbol rate and the chip rate must be higher than that of higher than or equal to or larger than equal to greater than equal to hop rate. Okay. So this is a condition for this frequency hopping. Okay. So in fast FHMFSK, there are multiple hops per M array symbol. Already know M array is equal to M equal to power K. In general, the fast frequency hopping is used to defeat a smart jammer tactic that involves two functions: measurement of the spectral content of the transmit signal and returning of the interfering signal to the portion of the frequency band. Okay, so here the frequency hopping is defeat the jammer's tactic by using two functions. One is the measurement of spectral component, and again return to the interfering signals to the portion of frequency. So at what portion it is going to interfere. Okay, so these are the two functions. And clearly, to overcome the jammer, the transmit signal must be hopped to a new carrier frequency before the jammer is able to complete the process of these two steps. So that is the jammer duty. The jammer, which is going to enter the spectral content and is going to measure the spectral content and again return to the which frequency is going to introduce to interference. Okay. So this is a jammer function. So whenever the jammer calculated first, again the transmit signal jumping to the another new carrier frequency. So that is difficult to the jammer or anyone. It is going to catch the signal. Okay. Synchronization. So here a solution to the synchronization problem consists of two parts. One is acquisition, tracking. So here we are using at the transmitter and receiver the pseudo noise sequence, simply can call as PN sequence. So typically PN acquisition proceeds in two steps. First, the received signal is multiplied by a locally generated PN code to produce a measure of correlation between it and the PN code used in the transmitter. Why? Because in earlier we can see two types of that means two types means one is a transmitter and another is a receiver. So the two parts is used the same PN sequence. Okay. So for that, the first the received signal is multiplied by a locally generated PN code to produce a measure of correlation between it and the PN code using the transmitter. So that is the acquisition. Next, an appropriate decision rule and such strategy is used to process the measure of correlation. So uptime to determine whether the two codes are in synchronism and what to do if they are not. Okay. And for tracking, it is accomplished using phase lock techniques. That is, PLL, phase lock loops. By using this phase lock loop, they are going to track. So one is a Here the first one is synchronization. In synchronization, we're having the acquisition and tracking. So for synchronous problem, we are going to use these two parts. One is acquisition part. That means we are going to acquire that signal and then we are going to track. Now the pseudo noise sequence. So what is the pseudo noise sequence and how the pseudo noise sequence is going to generate and what are the properties of this pseudo noise sequence have. Okay. So firstly, the pseudo noise sequence is a periodic binary sequence with a noise like waveform that is generated by means of a feedback shift register. That means here we are using the feedback shift register. So the feedback shift register consists of M flip-flops and a logic circuit. So flip-flops are regulated by a single timing clock. The state of each flip-flop is shifted to the next one. That means for every one clock tick, the flip-flop state is changes from one state to another. Okay. So this is the picture we can use. So here you can see the flip-flops, M flip-flops and a logic circuit. That is these flip-flops is going to connect to a logic circuit and the flip-flop state is going to change by using this clock. For every clock pulse, this state of the flip-flop changes from one to another. So with each clock pulse, the logic circuit computes a Boolean function of the states of the flip-flops. So the result is then fed back as the input to the first flip-flop, thereby preventing the shift register from emptying. The PN sequence so generated is determined by the length M of the shift register, its initial state and the feedback logic. So this is how this circuit works. Okay. So therefore the PN sequence produced at the output of the final flip-flop in the shift register. Why? I am using M flip-flops. So here with the total number of M flip-flops, the number of possible states of the shift register is at most 2 to the power of M. Therefore, the PN sequence generated by a feedback shift register must eventually become periodic with a period of at most 2 to the power of M. Why? Here M is the number of flip-flops used in this circuit. Okay. So this is a pseudo noise sequence generation. Now the properties. So here we are having two properties. Mainly you can say one is a balance and a run property. So in the balance property, in each period of a maximum length sequence, the number of ones is always 1 more than the number of zeros. So this property is called balance property. So the number of ones. Why here the pseudo noise sequence is nothing but with a combination of ones, zeros like this. So this is the sequence. Okay. So here O number of ones are required like this. So for this is 7 bit, 4 ones are there. Okay. And second one, among the runs of ones and zeros in each period of maximum length sequence, 1/2 the runs of each kind of length 1 and 1/4 are length 2 and 1/8 of length 3 and so on as long as these functions represent meaningful numbers of runs. So this property is called run property. So the pseudo is having two properties. One is a balance property and another is a run property. So the content of this information is totally taken from the Community Systems by Simon Hacking, third edition, and again Digital Communications by Simon Hacking, and some of the content from taken as internet. Okay, so thank you.
Like, share, and subscribe. Hit the bell icon for more updates.